Good morning, welcome to new lecture. Today I will review several examples. Let's look at the first one. We have this beam. First we want to find degree of indeterminacy and to see how many degrees this system is indeterminate. Then we will look at to see it is stable or unstable. As you know, degree of indeterminacy is equal to 3 times of member plus reaction minus 3 times of no plus condition equation. Here, number of members 1, 2, 3. Number of reactions 2 here, 4. Number of nodes 1, 2, 3, 4. Number of condition equations, because 2 member comes to hint, the number of condition equation is 1. If you know the number of members comes to the one hint, it is m. The condition equation will be m minus 1. Because here we have 2 members and we know from the beginning the moment here is equal to 0. So one condition equation, it is known, we know internal moment, one internal force here is equal to 0. So we know the magnitude of one internal force, so C is equal to 1. Now, in order to see how many degrees this system is indeterminate, 3 times m will be 9 plus 4 minus 3 times n, 12 plus 1. From here, this will be 13. Minus 13 will be equal to 0. So this system, it is not indeterminate. And degree of indeterminacy is equal to 0. But how about it is stable or unstable system? You see it is unstable system because if you apply a small load here, this structure will deform like this. So it is unstable system. This member can rotate respect, for example, A, B, C, D. A, B will rotate respect to A, so point B will transfer to the point B prime. So member BD will rotate respect to C, and for that reason it is unstable. So this system is unstable. Let's look at the next example. Next beam, next structure is like this. We have 2 members, we have rigid joint here, 1 hinge support here, another roller support here. First we want to see this system is stable or unstable. Here we have 2 reactions, here we have 1 reaction. But if you continue this reaction, all reactions, they are concurrent in one point. They reach to each other in one point. So this system can rotate. So it is unstable. Now, how about how many degrees it is indeterminate? M is equal to 2, 1, 2 member. R, number of reaction, 1 here, 2 here, it is 3. N, number of nodes, 1, 2, 3. See, condition equation here is 0 because we don't have any internal roller or internal hinge. So we don't know any internal force is equal to 0 from beginning. From here, this will be equal to 3 times 2, 6 plus 3 minus 3m plus r minus 3n plus 0. This will be equal to 0, but it is unstable. Let's look at the next one. Next one, it is this system. Fixed support, hinge support. We have another member here. Again, this is hinge support. For example, A, B, C, D. We have 3 reactions here. We have 2 reactions here. And we have 2 reactions here. The reactions, they are not parallel, they are not concurrent in one point. And if you look at, you see, this system is stable. Because this cantilever part, it is stable. We attach BC to the AB because AB part, it is stable, will make BC is stable too. BD will be stable as well. M, number of members here, 1, 2, 3 members. R, number of reaction, 3 plus 2, 5 plus 2, 7. N, number of nodes, 1, 2, 3, 4. 4 nodes we have. Condition equation, we have 3 members, reach to 1 hinge. So 3 minus 1, 2 condition equations here. So this system, degree of indeterminacy is equal to 3 times m, 9, plus 7, minus 3 times 4, 12, plus 2. That will be equal to 2. So it is 2 degree indeterminate. Let's look at the next one. Next one is this system. And we have one closed loop here. From beginning we see this is stable because it is this part, it is simply supported beam. We weld one loop here. Simply supported beam, it is not indeterminate. But one closed loop, it is 3 degree indeterminate. So this is stable and 3 degree indeterminate. But let's follow the formula. M will be equal to here 1, 2, 3, 4, 5, 6. R, number of reaction, 2 here, 1 here, 3. N, number of nodes, 1, 2, 3, 4, 5, 6. Condition equation is 0. So if we plug here, it will be 3 times m, 18, plus 3, minus 3 times n, 18, plus 0. This will be 3 degree indeterminate. Next one. Next one, it is this system. Here, this part AB is simply supported beam, it is stable. This part we attach to that. If we don't have this support, this can rotate respect to this hinge, and at the same time it can move in the horizontal direction. But after we put this hinge support, it cannot rotate and it cannot move, so it is a stable system. Let's look at to degree of indeterminacy. The number of members 1, 2, 3, 4, 5, 6. Reactions 2 here, 1 here, 3, 2 here, 5. And number of nodes 1, 2, 3, 4, 5, 6, 7. See number of condition equation. This AB part, it is continuous. This part, this hinge is like this. Here one internal force, it is moment is equal to 0. We know. Another things, this can move. This is internal roller. It can move in horizontal direction. So the shear force for here is equal to 0, 2. So the C here is equal to 2. If we plug in formula, we will have 3 times M, 18, plus R, 5, minus 3 times 7, 21, plus 2. Answer will be 23 minus 23 is equal to 0. Next one, we have this beam. Okay, how many members do we have here? 1, 2 members. Reactions, hinge support, 2 plus 2, 4. Number of nodes, 1, 2, 3 nodes. C, it is not internal hinge, it is internal roller. It can rotate respect to each other, and it can move in horizontal direction. So this system, if we apply axial force, it can move. If we apply moment, it can rotate. So two internal forces are 0. C is equal to, so for this system, DOI, degree of indeterminacy, is equal to 3 times M, 6 plus R, minus 3 times N, 9 plus 2. That will be equal to 10 minus 11, negative 1. So it is kinematics system. It is not a stable system, and you see degree of indeterminacy is equal to negative 1. Let's look at the next problem. We want to find reactions, draw moment diagram and shear diagram. Simple example, but I don't know why most students they have hard time to draw moment and shear diagram. During years, I am teaching statics, mechanics of deformable body, structural analysis for several years, and I see unfortunately most students, they have problem here. They don't know how to draw internal forces diagrams, and this is very important topic. You should practice a lot. And it is very easy. If you practice, you will learn. We have this beam, A point, for example, here let's put B, C, D. This beam is subjected to uniform distributed load. Uniform distributed load intensity, it is 8 kips per feet. We have one concentrated load here. It is 14 kips, and we have another concentrated load here. It is 10 kips. Let's look at to the length. From A to B it is 3 feet. From B to C 3 feet. From C to D it is 2 feet. We want to find reactions. We want to find shear diagram and moment diagram. It is very easy. First we will find reaction. There is no force in horizontal direction because there is no external force. In horizontal direction, summation of forces in x direction is equal to 0. So AX plus, there is no forces, is equal to 0. AX is equal to 0. We know that. This is AY, this is CY. Summation of forces in vertical direction is equal to 0. This will be AY plus CY minus 14 minus 10 minus 8 times the length. Length here 3 plus 3, 6 plus 2, 8. 8 times 8. Area underneath of this, it is rectangular 8 height. The length is 8. 8 times 8 will be resultant force is equal to 0. Summation of moment respect to one point is equal to 0. For example, point A, and I assume external moment counterclockwise is positive, is equal to 0. So I will have Cy times 6. Cy times 6. It wants to rotate this beam respect to point A counterclockwise, so positive, minus 14 times 3. 14 times 3 wants to rotate this beam respect to point A clockwise, so negative, minus 10 times 8. Load times distance, and the direction of load and distance should be perpendicular. It will create moment in 2 dimensions. So in 2 dimension system, 10 times 8, it wants to rotate this beam respect to point A clockwise, so negative, minus 8, the uniform distributed load intensity times the length 8. This will be resultant force. We are taking moment respect to point A. Resultant force will be 8 times 8 times the distance from centroid up to A. So 8 times 8 will be resultant force times, this is rectangular, resultant force will be in the centroid of that rectangular. The centroid of that rectangular will be in half distance. So from point A to the point of the resultant force, it will be 8 times 8 times 4 is equal to 0. From here you can find Cy. If you plug in this equation, you will find Ay. If you do this, you will find Cy is equal to 63 kips and Ay is 25 kips. So we know Ay is 25 kips, Cy is equal to 63 kips. Now, for beginner, those they don't know concept for nav and they don't have enough practice, the best way in order to draw shear diagram and moment diagram, using free body diagram. You should use free body diagram. But that is good for a statics course. Here you should be a little bit, you are in advanced level, you should be able to draw it very fast. For shear diagram, as I mentioned several times, it is good you move on this beam from left to right. You will start from left side of the beam, you will move to the right side. So as much as reaction, you will move in the reaction direction 25 upward. From point A, you will go up 25 kips. After that, if you move from left to right in this direction, in each step you are moving, you have downward load. So it means with constant slope, you should decrease that. Up to point B, what is the downward force? It is 8 times 3 downward. It will be 24. So here, if you come from point A to point B, with constant slope, you should decrease that and you should come to the 1, because 25 upward, 24 downward. So here, this will be straight line, diagonal line. This will be 1. Then we have 14 kips. So from positive 1, you will move down 14. So this is positive 1, positive 14 down. This will be negative 12. Negative 13, sorry, negative 13. Then again from B to C, you should move down in this load direction. 8 times 3, 24. So from here to here, with constant slope, you will move down 24. 24 plus 13, it will be 37. So you will reach to 37 negative. Then 63 upward. You will move 63 from this point up. If you moved 63 up, this is negative 37, you will reach to positive 26. Again from C to D you have downward, so 8 times 2, 16. You will decrease that to the 10. Here you will move 10 down and you will close the diagram. This will be shear force diagram. You see under concentrated load, the shear diagram will snap as much as concentrated load, and because this is distributed load, so shear diagram should be diagonal line. The derivative of the shear will be external load. So the derivative of diagonal line will be horizontal line. That is right. Now about moment diagram. Moment at point A, it is equal to 0. We know that. Why? Because point A is hinge. The definition of hinge, it means internal moment there is equal to 0. There is no resistance against the moment. So point A, moment is equal to 0. From point A to B, what will be the moment? First of all, the derivative of moment respect to the x will be shear force. We know that the shear force diagram is diagonal line or straight line and with constant slope. So the moment diagram should be curve shape, second order or parabolic. We know the moment diagram should be curve shape. If I move from A to the B side, just before B, let's see what is the moment. If I cut it, internal moment here, mx, from here to here, it is 3. Here, reaction is 25, and you have external force. External force intensity is 8. Let's see just before B here. what is the internal moment? If I take moment respect to point O1, always we will take moment respect to the cut point. I will have mx minus 25 times 3 plus 8 times 3 times half of 3, it will be from resultant force location to point O1, it will be 1.5 is equal to 0. From there, mx will be equal to 13.9 kips feet. And it is positive or negative. Here from this equation you see it should be positive, but on the other hand this moment creates tension underneath of the beam. Tension underneath of the beam, it means positive moment, so it should be positive moment, curvy shape, positive moment, and the magnitude it is 39. Now let's see how we can continue. Again, I can move from any direction. If I move from A to B, it will get a little bit complicated, so I can start this time from D. D is free end. In free end, always internal moment is equal to 0. If we apply concentrated moment, it will be as much as that concentrated moment. But here we don't have any concentrated moment, so the moment, internal moment here is equal to 0. From D to C, if I move, what is the moment? The moment will be 10 times just before C. This is free body diagram. 10, 8, I cut it, this is mx. It will be 10 times 2, you see, mx plus negative mx, because this is clockwise, minus 10 times 2 plus, negative. I'm taking moment respect to cut point, point O2 for example. mx it is clockwise negative, minus 10 times 2 minus 8 times 2 times 1 is equal to 0. From here, 10 times 2 will be 20, this will be 16. If I add together, it will be 36. If I take the other side, it will be negative 36. Negative 36. From equation we see it is negative. On the other hand, this beam, how deform here? It will deform like this. If deform beam deforms like this, underneath of the beam, it is subjected to compression. So, compression underneath of the beam, it is negative moment. From here to here, we know it should be parabolic shape. So, with one curve, I can attach together. This will be our moment diagram. This is our moment diagram. And you see, this is parabolic shape, linear parabolic shape. And from, for example, point C to D, the slope of this curve should decrease. Why? Because the slope of this curve, it is shear force. Shear force from C to D is decreasing. Now, if we move from A to B, moment is increasing, shear should be positive. Moment decreasing, shear should be negative. Moment is increasing. How it is increasing? The absolute magnitude, it is decreasing. But if we consider the negative sign, for example, negative 36 is less than negative 3. So here, for example, if negative 3 is greater than 36, so if we consider the sign, the moment is increasing. Shear should be positive. This is about that beam moment and shear diagram. Let's look at the frame. A, B, C, D, 20 kilonewton, 10 here, we have distributed load, but it is not uniform. It is variation is linear, triangle shape, distributed load. The maximum one, it is 10 kilonewton per meter. This is 20 kilonewton. From A to B it is 10 meter. And from B to C it is 3 meter. And from C to D again it is 3 meter. This is our frame. We want to draw moment diagram and shear diagram. Let's say write 10 like here. The magnitude of this, it is 10 kilonewton per meter. First step, I should find reactions here. If I want to find reaction, 8y will be equal to 20y. Summation of force in vertical direction is equal to 0. Ay minus 20 is equal to 0. So Ay will be 20 kilonewton. Ax, summation of forces in horizontal direction is equal to 0. In horizontal direction, if I write equilibrium equation, what I have the area underneath of that triangle, 10 times 10 times half area minus Ax is equal to 0. From there, Ax will be 50 kilonewton. How about MA, moment reaction at point A? If I take moment respect to point A, what I will have MA minus 20 times 3 minus 10 times 10 times half times 1/3 of 10. That will be equal to, from there, MA will be equal to 226.67 kilonewton meter. I'm taking moment respect to point A. I have MA, reaction, MA, counterclockwise, positive, MA, minus 20 times 3, the distance of 20 from point A, in perpendicular direction to the 20 force, it is 3 meter, 20 times 3, minus 10 times 10 times half area underneath of this triangle. This is resultant force. Where is the resultant force? Location. From that location to point A, if I multiply, I will have moment. Resultant force location is the centroid of this triangle. The centroid of one triangle, if this is L, the centroid distance from this side, it will be 1/3L. From this tip will be 2/3L. So because we are taking moment respect to point A, it will be 1/3 times L, it is 10. So first we will find reactions. I found reactions 226.67 kilonewton meter. Then let's look at the shear diagram and moment diagram. Shear diagram, moment diagram. Shear diagram, assume dash the line like this, it is inside of the frame, and I'm moving from A to B, from B to D. I'm moving, rotating clockwise like this. Let's see what is happening. At point A, the shear, it is equal to 50 because this 50 is perpendicular to the beam, force perpendicular to the beam or column. If I call this is beam column, force perpendicular to the AB element will produce shear. So here it is 50. So at point A it is 50. I will move in the 50 direction, from right to left 50. Then derivative of shear, it is external load, and external load variation, it is inclined line. 1 degree higher, it will be second order. So the shear diagram should be second order. Here, if I move from A to B, at point B, I have 50 kilonewton from right to left minus area underneath of this triangle, 10 times 10 times half from left to right. So they will cancel each other, it will reach to the zero, and the variation should be parabolic. At point B, this 20 reaction is perpendicular to this BD element. So I will move up 20. There is no force from B to C. I will continue 20 down. This is 0. This will be our shear diagram. So this is 50 kilonewton and this will be 20 kilonewton. About moment diagram. Moment diagram in this region AB should be cubic shape. At BC range should be linear diagonal because one order should be higher than this. Let's look at to the moment. At point D, moment is 0 because it is free end. From D to C, if I move, just before C, if I cut it, there is no force, so moment will remain 0. Up to point C, D, C. Point C, moment is 0. Point B, from C to B, if I move, just before B, here if I cut it, M, B, this is 20, from here to here it is 3. So if I take moment respect to cut point, what I have, 20 times 3. Negative or positive? Negative. Why? Because this 20 times 3 it is in this direction. If I rotate this beam in this direction, counterclockwise, it creates compression in dashed line. Compression in dashed line means negative moment, so it will be negative 60. This joint B is rigid joint. So if I have any moment in this side, that will transfer to other side because that rigid joint should be in equilibrium. Summation of moment at rigid joint should be equal to 0. So if this is negative 60 here, the moment, in this column, moment should be again negative 60. Moment at support, You see it is 226.67. If with rand, you put rand in point A and rotates in this moment direction. That create compression again in dashed line, means negative moment. 226.67. Variation from A to B should be 1 degree higher the shear diagram, so cubic shape, something like this, negative. This will be moment diagram, this will be our shear diagram. Let's look at the next example. Next example, we want to solve that system using superposition. It is a very simple example. We have this beam, 1 degree indeterminate. So using equilibrium equation, we will not able to find reactions A, B, here, distributed load intensity is lowercase w, pound per feet, for example. This length is L feet, EI is constant. We want to find reaction here. Because this system is 1 degree indeterminate, we are not able to find reactions using equilibrium equation. So, why? Because here, 3 reactions we have here. AY, AX, MA. One reaction we have here, RB or BY. Now, we have 4 reactions which they are unknown. We have 3 equilibrium equations. Summation of force in horizontal direction is equal to 0. Summation of force in vertical direction is equal to 0. And summation of moment, for example, with respect to point B is equal to 0. 3 equations, 4 unknown we cannot find. So, how many unknown? We have more than equation, 1 unknown. So, 1 degree it is indeterminate. Now, in order to find another equation, we need equation from deformation or compatibility equation. So, I should consider deformation. In order to consider deformation, the best way in order to approach this problem is superposition. I will assume I have one cantilever beam subjected to distributed load. The distributed load, it is, the intensity is W, plus I have the same cantilever beam subjected to reaction as a concentrated load at point B. If I add these two systems together, if I add this to this one, I will get our real structure. So let's look at the behavior one by one. If I have this system, what will happen? Point A, point B. After deformation, point B will move down to point B prime, and here I will have delta B1 deformation downward. If I have this RB at the end of cantilever, what will happen? This cantilever beam should deform like this upward, and point B should move up, and I should have deformation here like delta B2. But if I look at the real system, what is the deformation? Deformation will be something like this. Point A will not move up or down and will not be rotate. Point B, will not move up or down, and the formation at point point B is equal to 0. That means delta B1 downward should be equal to delta B2 upward. What is delta B1? Delta B1 is deflection in cantilever beam subjected to uniform distributed load. Previously I proved the deflection here, it will be W L to the power of 4 over 8 EI. What is delta B2? Delta B2, it is cantilever beam subjected to concentrated load at the end or free side. So what will be deflection? Previously we saw that it is R B load L cube over 3 EI. These two, they should be equal. So if I plug these equal, W L to the power of 4 over 8 EI is equal to RB L cube over 3 EI. EI and EI from both sides, they will cancel each other. This L cube with this L4 will be L. So reaction at point B will be W times L times 3, so 3WL over 8. The reaction here will be 3WL over 8. So I found reaction here. It will be 3WL over 8. Now after finding this reaction, others we can find using equilibrium equation. Summation of forces in the vertical direction is equal to 0, means AY plus RB minus W times L is equal to 0. I can find AY. Summation of force in horizontal direction is equal to 0. AX is equal to 0. We know that. Summation of moment respect to point B, for example, is equal to 0. Because now I have AY, I can take moment respect to point B, will be MA plus W times L over 2 minus AY times L is equal to 0. Let's I write those. Summation of forces in horizontal direction is equal to 0. AX is equal to 0. Summation of forces in y direction equal to 0 will be AY plus RB minus W times L is equal to 0. Summation of moment respect to point point B is equal to 0. I have MA plus W times L over 2 minus AY times L is equal to 0. So I can find AX, I can find AY, I will plug here, I will find MA. Let's look at the next example. Next example, we want to draw conjugate beam for real beam. So we have real beam, we want to draw conjugate beam for those. Real beam, I want to draw conjugate beam. Real beam is simply supported beam. The conjugate beam will be the same. Real beam is cantilever beam. Conjugate beam, the fixed support will convert to free to the fixed. Both end fixed will be both end free. We have hinge support here, roller support here. Free will be fixed. This is hinge support will be internal hinge. This is here, roller will be internal hinge. Free will be fixed. Let's look at two. These beams. Fixed to free and hinge will remain same. Fix will be converted to the free. Internal roller will be here, internal hinge, free to fix. So A, B, C, D. A will remain the same. B will be internal hinge. C will be internal hinge. D will remain the same. This is, you should pay attention to the concept. Then, if you practice, it is easy to figure out what is the real beam, what is the conjugate beam. If we have conjugate beam, we can draw real beam. If we have real beam, we can draw conjugate beam. Let's look at this example. We have this beam. A, B, C, D. 3 meter, 3 meter, 3 meter, 25 kilonewton. Okay, we have this beam. This beam is subjected to point load 25 kilonewton at point C. EI is constant. We want to find deflection at point C. Deflection at point C, and we want to find that using conjugate beam method. First step, we should find moment diagram. In order to find moment diagram, we need reactions. We should find dy, we should find ay, and we should find ma. and we know AX is equal to 0. dy, it is very simple to find because BD part, it is like simply supported 25 at midspan, so 12.5 will be contribution of support D, 12.5 will be contribution of part B. You can find like that, or if you are not able to figure out like that, you can find using equilibrium equation. If we want to find dy, I can take moment for right side respect to point B equal to 0. That will be dy times 6 minus 25 times 3 is equal to 0. From here, I took the moment respect to point B, because point B it is internal hinge, and we know in the internal hinge moment is equal to 0, so I can put equal to the 0. And I wrote that for only right side. So from there, dy will be 12.5 kilonewton. If I write summation of force in vertical direction, AY plus dy minus 25, it is equal to 0. From there, it is AY, it is equal to 12.5. Of course, without of that you can find it. It is very simple system. This BD it is simply supported part, so half will transfer to the D 12.5, half to point B in vertical direction 12.5, and that will transfer to the AY 12.5 upward. But if you are not able to follow like that, you can write equilibrium equation. Now if I want to find MA, I can take moment again respect to point B for left side. That will be negative M. That will be negative MA plus, negative MA minus, I made a mistake, MA, if I take moment respect to point B is equal to 0 for left side. What I have MA counterclockwise positive minus 12.5 times 3 clockwise negative is equal to 0. From there, MA I can find it will be equal to 37.5 kilonewton meter. So I have reactions now. So I can draw the moment diagram. Moment diagram for this system, it is very easy. Moment at point D is equal to 0. Why? Because it is hinged, there is no concentrated moment. So internal moment here is 0. Moment at point C is equal to positive 12.5 times 3. So it will be positive 37.5. At B it is internal hinge, it is 0. There is no force in AB, BC, CD part, so the moment diagram should be linear. At point A, again the moment is negative 37.5. Negative. Why negative? Because imagine with rand, you take point, you put rand at point A, you rotate in this direction. That will create compression underneath of the beam, so it is negative internal moment. So the moment diagram there should be negative. This is our moment diagram. Now I should draw the conjugate beam for this beam. Fix will be free. This point B, I will have internal, I I will have internal hinge support. D will remain the same. So A, B, C, D. Moment diagram divided by EI moment diagram divided by EI will be load on this conjugate beam. So moment diagram 37.5 divided by EI. 37.5 divided by EI. I will divide moment diagram by EI and I will apply that as a load to conjugate beam. Here moment diagram is positive, so the load should be upward. Here moment diagram is negative, the load should be downward. Now, here we want to find, in real beam we want to find deflection at point C. It means in conjugate beam we should find internal moment at point C. That internal moment at point C will give us the deformation at point C. So first step, I should find reaction. I should find dy, and dy here will be downward. Then after finding dy, I can find internal moment at point C. Let's first find the dy. If I want to find dy, I can take moment respect to point B. So summation of moment respect to the B is equal to 0. What I have, let's see, dy times 6, this is 6, dy times 6, it wants to rotate this beam clockwise, so negative dy times 6 plus moment because of this triangle, it wants to rotate this beam respect to point B counterclockwise, so positive. It will be area underneath of that triangle, 37.5 divided by EI, that is height, times 6 times half, that will be area for this triangle. Because it is symmetrical triangle, the centroid should be at point C, times the distance from centroid to point B, it will be 3 plus moment created by this triangle load respect to point B. Again, it wants to rotate this beam counterclockwise, so positive 37.5 divided by EI times 3 times half, this is area, times 2 over 3 times 3 is equal to 0. Area 37.5 divided by EI times 3 times half. The centroid distance up to point B, it will be 2/3 of L. So 2/3 times 3 is equal to 0. You can find from there dy. Now we want to find internal moment at point C. We can draw free body diagram. C, D, this is dy. Load, it is in this direction. I will cut at point C. Internal moment here will give us delta C. So I should take moment respect to point C. If I take moment respect to point C, because now I have dy, I can do that. Let's say take moment respect to point C, cut point, because we want to find the deflection here, and internal moment at point C in conjugate beam will be equal to the deflection at point C in real beam. So that will be, let's see, that will be delta C negative plus delta C negative clockwise minus dy times 3, a distance, both delta C and dy times t, both times 3, both of them clockwise, negative, negative, plus the moment of this distributed load, non-uniform distributed load, will be counterclockwise. It will rotate CD counterclockwise. So positive. The height here, it is 37.5 divided by EI. So area 37.5 over EI times 3 times half, this will be area, times 1/3 of 3 is equal to 0. From here you can find delta C deflection at point C. Okay, I think it is enough for today. Thank you so much for watching this lecture. See you next session. Bye bye.